I think you're still under the early bird portion of that workshop. So if you are interested, please do join. Let me see if I can share my screen. Okay, so folks can probably see my screen here. This is the deep learning workshop, and I'm going to share the link to the workshop next week. All right, okay. All right, I'm going to stop here and ask Ravi to please start off with a quick introduction or long introduction, set the stage, and take it on from here. And again, thank you, Ravi, for spending your time and helping us with these learnings. Much appreciated. Ravi, off to you.
Hello, can you see my screen?
Yes, we can, Ravi.
Oh, great. Good morning. Thank you, Yash, for kicking this off. It's 10:15. We have 1 hour and 15 minutes. So what we'll do now, this is kind of a deep learning for NLP with PyTorch. So we'll probably spend around an hour. You can make it interactive. You can ask your questions in the chat and other things. I'll just say a few words about NLP, the challenges and the approach people are taking in NLP, the tools out there. And then we'll probably see a couple of examples using PyTorch, right? How PyTorch can help in solving NLP or natural language processing. That's what we're going to do. And in case you're not in a position to hear it or not seeing the screen properly, let me know. I'm going to go into the full share mode here. Okay, all right. Hopefully you can see the screen. All right, the topics: NLP introduction, some NLP tools and pipeline. How does it look? And also, how do we use PyTorch for NLP problems? This is my bio. I've been working in the Silicon Valley for quite some time, and currently I'm a lead data scientist in a stealth startup in Santa Clara. All right, so let's get on to this popular AI. I've shown a few things in terms of how AI has become part of our life without we realizing how quickly it has become all over the place. You see AI being used all over the place. 10 years ago, that was not the case. Things have changed a lot. Netflix, Pandora, your Amazon buying experience, Alexa, you name it, everywhere is the self-driving cars, of course. So what is machine learning? Machine learning is basically it can do certain tasks without explicit programming. That's what it is. I won't spend too much time on this. It's a typical pipeline for machine learning, which is supervised machine learning, where we have labeled data, which is having information. Typically, data, when we talk data, it's all numbers, sometimes could be words, particularly numbers. And it also knows for every piece of data what the outcome is supposed to be. And the machine learning algorithm will learn the function, which relates the label and actually the data. And then we use the machine learning model for prediction purposes. That's why we are doing it. Simple examples of supervised learnings are, the Monday stock prices. Can we predict tomorrow's stock price, right? So what do we know? Based on what we know, we create a model, and then we start predicting based on the model. I'm just quickly going through the basics of machine learning. There's a task in a computer vision. In this case, there's a picture of presidents. You're supposed to predict which president it is. The picture is converted into a pixel representation, which becomes a set of numbers. And then you run a classification model and come out with the probability of each president. Whichever president has the maximum probability, that's what the prediction does. This is how machine learning works in terms of taking a data in real life, like picture, converts that into a numerical representation, and your model is based on the machine learning model is based on the numerical data, right? That's what it is. This is all good with numbers, right? Age, salary, pixel intensity, those kind of things. Now we are talking about NLP. NLP is all words. It's not numbers, all words, right? That's the beauty of natural language processing. So basically, this is the Wikipedia definition of NLP. It's a subfield of linguistics, computer science, information engineering, and artificial intelligence, concerned with interaction between computers and human languages. In particular, how to program computers to process and analyze large amounts of natural language data. Right? Language data is pretty tricky. It's not a pretty straightforward numbers where it's all ordered. We know what it is. So the language piece is much more difficult than what we think it is. In terms of looking at the landscape, about 80% of the data in organizations are in text format. All kinds of text, emails. Emails has lots and lots of information, chat information, documents, PDF documents, and even voice recordings. These are all text data, can be converted into text data. It is hard to analyze the structured data. Structured data is pretty easy to analyze, but this is unstructured, right? Plenty of papers are getting published every day, and this field is getting more and more fascinating as we speak. Some more numbers. It's like 6 billion. Is it 6 billion? Yeah, 6.5. This is the old number. It could be much lot more. A lot more web search is done every day, right? And all these are pretty much using NLP. It's all unstructured data, which is converted into some kind of machine readable format, and then the search is done and you get back the results. So we use NLP to a certain extent every day, right? Spam detection is something which happens. Basically your document and the words in your documents are based on the frequency, and a supervised algorithm basically figures out the likelihood of your mail being a spam or not, and it happens in your daily everyday emails. It happens, right? And it's pretty good. You know that very rarely you see a good email getting into spam, but some spam could get into email. That's by design, just to make sure that you don't have good emails getting into spam folder. So we use NLP based algorithms in all kinds of ways. Some more interesting areas, speech recognition, it's very good nowadays. Online chatbots, nowadays when you're chatting with some companies, say customer representative, most probably you're talking to a chatbot, right, to start with at least. Text summarization, if you have a big paragraph for text, summarize it and give the short version of it, that NLP algorithms can do it. Auto-generated keyword tabs, right, when you're typing something, the next possible words come in, the best possible words, next one. These are all NLP based algorithms. Even code writing, when you write code, what is the next possible, the code, right? All these are auto-generated. These are all using machine learning and NLP algorithms. Identify sentiment of a text, good or bad, happy, those kind of things. Some more categorization of text, gathering news, analyzing contents, rerouting email based on the right person. This is pretty important in the corporate world. We get lots of emails, and you should have an easy way to prioritize and actually send it to multiple people. Especially this if the receiving email is a support email or something, right? It's not a person replying it. It has to go to the right person. Comprehending news article, I think we spoke about it before. So all these are all NLP real life examples. And the approach, how do you approach solving these problems? We can actually define rules. We can define rule to take a sentence, convert that sentence based on the grammar, what it is, then basically code it so that if this is what the sentence is, this is how the response is going to be. This will be lots and lots of rules, and it's pretty tough to implement. But that's how people are doing to a certain extent, to be honest. But that's pretty rule-based approach is very, very tough. Machine learning based is what we are talking about. Basically, we need to machine learns based on the given input and output. But this also is pretty tedious because you need to annotate lots and lots of data, right? It's very expensive, and training is very, very laborious, right? All these approaches. Then a few things about NLP is it's the learning. This one is hard, right? Learning language interpretation is very hard. Take a look at these sentences. I enjoy working in a bank. I enjoy working near a river bank, right? If you just use a bag of words approach, its only difference is I think the river is the difference. Pretty much the most of the sentence is the same, right? But they are not, right? The river bank and the bank means completely different things. So it's a question of learning the syntax, grammar, then the semantics of it, and then also comes the pragmatics, right? What that really the text is trying to say. That is very social, very regional, social, and language specific, right? What is actually it is trying to say? Even though you have a semantic meaning is something, it's actually meaning something else. So it's pretty hard to, and the context-based interpretation is pretty hard. The ambiguity is always, there is ambiguity is there. Dissolving ambiguity is hard because you have to do it correctly. I made her duck. This is another sentence, right? This is, again, I took it from some course literature, I think. I made a duck, I cooked waterfowl for a benefit. I cooked waterfowl belonging to her. I caused her to quickly lower her head or body. So there is a lot of meanings, interpretation for made a duck, right? Ducking means you can bend your so lower your body, right? That's one thing you can say. Or somebody cooks the duck, right? There are a lot of ways you can interpret this, even though it all depends on the context, right? That's what the ambiguity means. So I won't spend too much time on this. You get the idea, right? English is a complex language, so are a lot of other languages. The same sentence could mean different things, right? All right, and phonetics also comes into picture. If you add who is saying it, what kind of pronunciation it is, then it's different. I made her duck, right? It's like the Australian pronunciation. You can say that it's I made a duck. I am ate a duck, right? I made her duck. All look similar, right? So if you add the voice translation in addition to the language translation or machine interpretation of what's happening, it's really, really tough. And if you want to use this for decision-making purposes, you have to make sure that your algorithm and your model is pretty strong so it understands the context, gets the right meaning out of it, and actually responds. So it makes problem lot tougher than dealing with the straight numbers. Like now all these image representation of numbers represented by numbers and any other problems looks like a piece of cake when compared to what problems you have to solve just for looking at one simple sentence. Okay. Okay, this is extracting sentiment and social meaning, right? Lots of meaning is in the connotation. What is connotation? An idea or feeling that a word invokes in addition to its literal or primary meaning. We saw quite a few examples, right? A word or a sentence has its literal and primary meaning, but the idea or feeling, which is based on the context, is basically the connotation. And machine learning models can be used to derive this connotation, or sometimes it's called as sentiment analysis, right? So having spoken about quite a few things on this, let's take a look at a typical NLP pipeline, right? The idea here is we have to get from these complex sentences and words and come to some kind of a numerical or some kind of standard data structures, which then can be used by the machines. That's the idea, right? You have to get to that structure. So whenever we say NLP pipeline is to take the corpus or the documents or the sentences, and you produce representative data structures. That's the idea here, right? And this is a typical NLP pipeline, which is a sentence segmentation. First of all, you need to take a big essay or a document and come up with sentences, which is probably using full stops, right? You can just say, oh, this is sentence, this is a second sentence, third sentence. The second one is taking something called tokenization. Basically, you take a word or in whatever, right, coming, those kind of things. And basically you come up with what is the corresponding ID for this. So that's called a token. Every word will have an ID based on the dictionary. Then we take a look at, you start to tagging those words, which is called POS, stands for parts of speech. Right? You say whether it's a noun, verb, blah, 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 now those adjective, those kind of things, because that helps a machine learning model or whatever you want to do to deal with the word better, right? That's one. I'm not saying every machine learning model use this approach, but this is the approach most popular people do, and there are a lot of tools out there which help you doing it. There's something called lemmatization. Basically, you take a look at all the words and bring it to the root, right? Coming, come, came. It's all these are all different words, different tokens, but from a root word perspective, it all comes from come, right? So sometimes you want to take that approach as opposed to taking the different variations of it. Sometimes you don't. But these are something you need to decide as a data scientist what to do. Dependency parsing. This is basically the sentence you take that, which is where a verb, adjective, which noun is it acting on, those kind of things. Basically, it's a dependency parsing of a sentence. Then something called named entity recognition, right? In a sentence, you'll have a name, ACM, NLP, and all these names, right? Washington, DC, right? You don't want to train a model where things are taken, Chicago and Washington, DC are different, right? You may have to take it, they are different in a separate context. But in most of the cases, we need to know is somebody is referring to a city in that text. That's important. Some places, you're traveling from and to city, that's different. You need to know from where to where you're going. But in most of the places, it's enough to know that it's a named entity we're dealing with. So we don't have to we can just treat it as a entity and move forward. So you need to recognize that. That's called NER recognition. Then stop words, so these are the words which you don't want to confuse the model. Taking the asterisks, sometimes you do, sometimes you don't. Commas, some quotations, certain things. All these stop words may not mean anything, or some of the high frequency words like the, a, those kind of things. You can just remove it from your algorithm because these are not going to contribute to anything. But in some cases you don't, right? You make a choice on what to do. Noun phrases, co-reference, resolution, all these wonderful things you do. And once it is done, then you have a data set which is more clean and more tagged, to speak, in a loose manner. And this can be used for further processing. This is a typical NLP pipeline. Now comes more difficulties. Now it's not only language. People are just talking using hashtags and emojis and other things, right? So we may have to improvise our natural language processing, taking into account this latest generation of communication mechanism using emojis, right? I haven't seen a model which is using emojis yet. I think it's coming. It's probably out there. I have not used it yet. So kind of interesting. All right, let me keep going. How much time do we have? 10:33. I think we are good. I'll try to finish it up by 11. Oh, we're supposed to finish up by 11:30. By 11:15, I'll finish off. So we'll have some time for talking or questions. See, this is the example. Chinatown, Chow Town with Chan. Hashtag crab and hashtag pork. Hashtag Zia Lang Wo. Whatever. This means something, right? But machine learning models, if it wants to do a good job in as a chatbot, should be able to recognize all these kind of things. All right. Next comes what we have seen so far is somehow we have to get these words into a standard format, and then we have to start using these words as some kind of numbers, right? One way to think of using these words as numbers is give a number ID 1, 2, 3 for every one of those words and start using it, right? That's one way of doing it. Then if you think about this hard coding, if you have got 30,000 words in a vocabulary, it's typically what English has, 30,000 words, then you need a hard coding of a vector of 30,000 size for representing every word. That becomes a really sparse embedding, and it's tough, right? It may not be meaningful also, right? So what the word embedding does is it has a nice concept of converting a word into a vector. That's what it is. The idea here is this is the statement from J.R. Firth, 1957. You shall know a word by the company it keeps, right? So by looking at these sentences and looking at the banking, based on the corresponding words where the banking words occurs, and you can generally say that what this banking represents, right? It represents some debt problems, something to do with money, regulation, or like there are certain words which what banks can be related to, right? And that's how these vectors are formulated, which is called the word vectors, right? Word embeddings. So this is a quick intro to this. So the vector space model, right? For example, candy can be represented by a vector of size 8 using these numbers, right? So vectors represents a dense vector. In this case, we are using 8-dimensional, a vector of length 8 to represent the words. Let's keep going. And if you represent all these words with these vectors, let's assume it has got only 3 dimensions for illustration purposes. Let's see where, and if you start projecting these words in this 3-dimensional matrix, you can see dog and cat are together somewhere closer together when compared to a car. The idea is your vectors will bring the related words in whatever relationship they have together, and if they are dissimilar, it will be further. That's the idea, right? That's the idea of having this vector representation of models. Once you have this numerical representation, that's how we see it, our vector representation. It's called word embeddings. What else can it called? I think word embeddings is the most common term used. So if you have that, then you can use those vectors in your deep learning or other algorithms to develop machine learning models. All right. So here, some more. So a word's meaning is a point, a 300-dimensional space. In this case, the words, the vector length is 300, right? And if you come up with the 2-dimensional visualization of those words, you see mango, pineapple, banana, they're together. You can see it. Tolstoy, Gogol, right? I think Gogol is the way to represent. They're all writers, they're together. Lake and mountain, they are natural nature places or entities, they're all together, right? That's how these word embeddings work. Okay, so now we have an idea about how words are there. Words are getting represented as embeddings. So embeddings are the core of the NLP. That's the core, right? And the core technology of NLP task, question answering, machine translation, information retrieval, etc., is finding synonyms of the words. Decide if 2 sentences have similar meanings. Basically, look at the words and see words between the 2 words. Suppose let's talk about something like 2 sentences do they have the same meaning? One way to look at it is, okay, sentences got 5 words, got 6 words, and let's take a word by word and see how similar those words are. And come up with some kind of a distance measure, which represents, okay, this is the distance between these 2 sentences, irrespective of the arrangement of the words. Just see the distance, and you make it kind of a unit vector or something. It's not unit. It's just make sure that you would divide it by a scalar and make sure that it's not it ranges from 0 to 1. And if you do that for multiple sentences, then you can easily say which 2 sentences are similar, or you can rank at least the sentence in terms of similarity to the first one, and then figure out what to do. That's one way, easy way of doing it. But all these things require to start with a good set of embeddings and you need to figure out how to find out those vectors first, right? We thought we just random set of numbers. How do you actually find those vectors for these words, given the context that whether it's similar or not similar? That's where the word embeddings are the core to NLP. Actually, you train models to figure out the embeddings. That's part of the whole machine learning training too. All right. Any questions? I don't see any. Let me see that how I can see the questions here.
Ravi, we had a couple of hands raised.
Okay, let's pause for a second. Okay.
Yeah, I want to let people know that they may not be able to speak because of the webinar nature of this, and there's usually a lot of noise in the background. So, folks, please write your questions on the webinar chat or on the Slack channel, and we'll try to pipe it through. And so, if you raise your hand afterwards, I think, can we end about 10 minutes ahead or so and take some questions, Ravi, before the end of the seminar, and then we can selectively
Sure,
unmute people.
sure. I just saw one question. I'll just answer it, right?
Yeah.
So how do you represent words that have multiple meanings in embeddings, right? All right. So in this case, again, the word, there'll be only one word embedding in typically most of the models, right, for a given word. And if you want to see, one way to think about is when the word embeddings are created, they are created based on some context, right? Sorry about that. It's based on some context, right? So one way to think about it is when you're training the word for, say, for example, if you want to get a shorter version of a sentence or a news article pertaining to medical records, right? I'm just picking up an example, right? Medical records or politics or something like that. When you develop when you're actually train the model using that data, which is basically this is the patient history in terms of in a structured way of representation, and you want to derive information ABC out of this, and you train the whole model, and you start off with a given word embeddings from some language model, and let your machine learning model actually train the word embeddings too. In that case, it will start pointing towards the word embeddings for a word, because in a medical context, it will be different from a regular language context. It will automatically pick up the similarities and dissimilarities because you have started training it. That's one way to think about it, right? Again, I'm not answering your question on, hey, it really has multiple meanings, right? I'm not talking about a single meaning or a context. If per context, you can do it. Now, if it is having multiple meanings, you probably, as a word itself, you come up with the best possible representation from a language perspective, right? That's what the training will do, right? And you actually start using it along with its context, along with where it is being used in a sentence, right? You don't actually use just the words and start doing machine translation. That doesn't work that way. You start taking a look at the words in context with what is being along with the coexisting of other words. Then you, based on the combination of its existence with other words and where it is existing, then the machine will try to figure out what to do next, right? The what to do next could be, there is a missing word. I have to figure out what that word is. That could be one. Or the what to do next could be, I got a question I need to answer, right? It will figure it out. It all, because it's not based on a single word, it's a combination of words. That's how it's trained on. I hope I'm answering to the question. So you don't, if you have multiple meanings to the embeddings, naturally you cannot represent the same embeddings. No, it's not, it doesn't have a meaning one, meaning two, meaning three. That's not the case. It is actually the existence with the other words and the training which comes along with this decides the action. That's one long answer to that question. Second, a couple of more questions and I'll keep going. The other question is, what is co-reference resolution? I'm just thinking around here. I think it is basically within a sentence, you can refer to the same noun. I think I'm saying it right. In a when you say a long sentence, you can refer to the previous another word in that the same sentence using some her or him or whatever it is, right? You can refer to the another word, a noun probably, using a different using a different term. That kind of co-references can be picked up in the sentence itself. I believe I'm pretty sure that's what it is. Okay, it's basically, it gives you the relationship between the words that can be picked up while you don't want the machine to worry about this. You can actually pick it up and give it to it. And sometimes you don't have to, but that also helps. There's one more, I'll stop here. We can understand meanings of the sentences even if the speaker speaks grammatically incorrect sentences. How is this resolved in NLP when your base of the language is grammar of the languages? Yeah, that's a very good question, right? If your algorithm is not really based on, for example, if you use your came and come, those kind of words of the same, it's the same meaning, and if you train the model, machines will actually look for only the words, occurrence of the words, not necessarily the tense, to figure out that meaning, right? It can do that particular piece. That's one thing, one way you can think that machines can do. It's not actually looking for the exact grammar. It's not actually looking for the exact grammar. So it will do decently well in that particular situation. Then that's one way to answer the question. Basically, inherently, machines are actually not looking at the grammatic correctness of the sentence. It's just looking for the words and where they are placed. And even if there are some mistakes in terms of plural, singular, and other things, it can basically pick things up pretty well. It's one way to think about it. Another way to think about it is when you're training itself, you just make sure that you have more and more ugly data, right? Just make sure it's there. So your training data is not really everything from Shakespeare books or something. You take it from a commonly used language, right? What people use, and use that as your corpus. You're better off. Your machine will understand it and act accordingly. Okay, so I'm going to stop here at this point, and I'm going to move on to presentation. Okay. All right. Good questions. So embeddings are core of NLP. So good questions you're asking. As we go along towards the end of the lecture, you'll see that most of these basic problems have already been dealt, because we don't have the horsepower and the data to solve these problems. So companies like NVIDIA and Google, Facebook, they all solve this problem for us so that we can start using the models which they have developed and just use it, right? Which is a good thing. But it's good that you're asking these questions. All right. How to learn these embeddings, which is where we were all talking about, right? You know that mango and banana are together. Banana is further from Tolstoy, right? All these kind of things. I'll skip certain things. Okay, this is one good way of learning the words, right? It's called a continuous bag of words model. You may hear this term BOW, B-O-W. It's a bag of words model. It's basically here you're taking a look at I am eating good pizza now, right? And just assume you don't know how to represent I am eating good pizza now. You don't know all those kind of things, but you want to learn it. You want to learn it. So way to do that is just take these words and you start predicting a word, right? In this case, you want to mask eating, and using I am and good pizza now. Good pizza and I am. Try to predict eating. It's basically a 3-gram model. There are three words together, And within the three words, you know the two of them, and you're trying to predict the third one, right? You can see it up that way too, but it's basically a bag of words model. It's not an n-gram model, sorry. It's a bag of words model. You take a look at sentences, you mask a word, and try to predict it. And you start training your model based on a starting list of embeddings, and you refine your embeddings so that you can do a good job in predicting eating. So in that way, once the model gets trained, pizza, good, I am, now, all these words, will come up with a decent representation of numbers, I suppose some random numbers. That's the idea of this training, coming up with word embeddings. A deep learning model will look something like this. If you think about it, if you're assume your vocabulary is only 6 words at this point, just 6 words, which is here, and these 6 words, word embeddings are here, right? These are all these 6 words, and the embeddings has got, I think it has got, every embeddings is three. The length of the vector is 3, so that's the idea. So it's 6 words, every vector has got of length 3, and everything. You start off with a random set of embeddings for every one of these words, and you set up your deep learning layer. So this is basically, this is so confusing. It's nothing but it just picks the right embedding. The first one is 001, right? This is the and the I, and this is am, right? So it's picking up the right embedding, and this is eating. This is good, right? It's picking up the right embedding. So it's picking up the right embedding, and then it's using a regular, a simple deep learning network. It uses certain weights, and it comes up with a softmax layer, and it decides what the output is, right? The output here is, what is the maximum of this? It is deciding this is output, which is 0, this one. The actual label is here, so it's mismatch. Are you following this? If you're familiar with the deep learning networks, a softmax layer will produce the output. The idea here is it's supposed to predict the this word. This eating is the word it's supposed to predict. It's coming up with the softmax layer. This can be converted into whichever is the maximum gets 1, everything is 0. So it is 0, 0, 1, 0, 0. That's what it's coming to. And then that's the word it's predicting, right? And this is actual label. Of course, it's not correct, right? The deep learning network first comes up with some answer. It finds out, oh, there is a problem. It's not matching. It does the backward propagation to adjust these weights. It also adjusts these embeddings. It retrains again and again. We're just talking one sentence. There'll be multiple sentences going in. It'll be training again and again. Finally, these weights will get stabilized, and most importantly, we're looking for these embeddings to get stabilized so that it starts predicting the missing words correctly. Once it does the good job, then we know that the set of embeddings is here, and we will use it somewhere else. Now that embeddings is each 3 vector representing a word, and that's good enough to do other things. That's the idea behind how do you determine the embeddings. All right. So a lot more questions here. Slide 36. It's a good question here. In slide 36 is 00010 and embedding for am. Let me see. I am. Yeah, you're right. Oh, no, it's not the embedding. I'm sorry. Mistake here. Your question is 00010 an embedding for am? No, it's not. So it is actually it is a, you can say it is a code or hard code to represent the term. That's what it is, right? So if you take that one and multiply this particular matrix, it is the 1, 2, 3, 4, 5th vector. That is the embedding. It is actually clear in the next one. So this is where the training I talked about. Here it is. This is the, assume this is 0010, right? This is the last number. It's 001. It's 10. You multiply by, this is the W vector, which is shown here, right? This is the word embeddings. You multiply by that, you'll basically get this vector. 0.1, 0.5, and 0.3. And that is the embedding for AM. Fair enough? And 0001 is what? I. For I, the embedding is 0.2, 0.1, 0.13, and 0.23. If you multiply these two metrics, this is what you get. This hidden layer, this is nothing but the embedding. I hope this is clear. Okay, that's the key. If you understand this, then you're good. This is just this 001 is just to make sure you pick you represent this like a hard coding so this means this length of this vector in the real world will be the equivalent to your dictionary size. Our dictionary is 30,000 words in English dictionary. So the initial on the hard code for an English dictionary, it will be like 30,000 size vector. For every one of them, there will be a vector which is corresponding to that particular word. That's called word embeddings. I hope that's clear. So this is word embeddings, and this is the hard code representation for that word. Okay, it's also represented in a nice way so that you can multiply these two vectors and get the word embeddings by just doing it. All right, very good. This is a typical sequence model in a deep learning setup. This is your input. Encoder will see it will be a set of here. Now we know this these embeddings very well, right? Now I am a student will get converted into an embedding for I am a student, right? It's all good. Then you can have an encoder, which means it will go through a series of linear transformation. Probably can have a nonlinear transformations too, and it'll get the essence of what it represents. Then we'll have a decoder which takes these information and uses another set of embeddings, list of embeddings, or not embedding, list of dictionary basically for this particular language, and picks out the best possible words to represent this. And that's how your machine translation is done from English to another language. Decoder, encoder, decoder method. The word embeddings from here are used, and embeddings, I believe, from these can also be used as a can they be used? I'm just thinking aloud here. Don't necessarily have to use it. This is important. This one is the embeddings start with is important. These embeddings are not really important, but it needs to use the dictionary to pick up the right word. It's very, very important. That process, we may have to use the embeddings. I have to go and check. But you get the idea, right? The embeddings are more important. So I'll skip this and come back to this later. NLP pipeline will look something like this, right? You have documents, you do some kind of pre-processing, which is what I talked about. Yeah, you come up with these words, do lemmatization, then you POIs, parts of speech, tagging, all those wonderful kind of things you do. Then you use this word embeddings. Then you have all these wonderful network. The output could be what you want to do, which could be sentiment analysis or classification, entity recognition, translation, topic modeling, all those kind of things you do. But this is the one which is doing the trick. But the foundation for the trick is the word embeddings, which is used to represent the words. That's how the deep learning based NLP works. So along those lines, there are multiple types of deep learning models which were being used. I will quickly go through this. Can you see the screen? I'm not sure.
Yeah, I can see it. You're good.
LSTM working steps, right?
No. We can still see the NLP.
Okay, then I'll stick to this. I opened up another document. I'll just stick to this. Okay. So the kind of things, the way the whole thing progressed is because this whole, it's called sequence, right? Any sentence is sequence. It has got words in a certain order, right? You have to process in the words in certain order. It's like a time series processing. So the order of the word processing it means a lot. So people started using something called a recurrent neural network, which is called RNN. Then that was not good enough. And then we came up with this LSTM architecture, which is long and short term memory, where it will remember certain things. It won't it'll remember something from the short term words, nearby words, and some words from the long. It will start remembering those kind of things. So I hope everything is good. Okay, all right. So it will start using these kind of structures to come up with, to fill in the gaps of this particular deep learning models, because it has to learn the sequences. And I'm going to use I won't go through the LSTM architecture and everything. That's not the idea here. But if you develop a network using NLP, we can solve, using LSTM, we can solve some NLP related problem. And we are going to see a lab now. Okay, so you got a half an hour. I want to do 2 labs. We will have time.
Hey Ravi, before
yeah.
you move to the lab side, do you mind clicking on the Q&A tab in Zoom?
All right.
And then maybe quickly running through some of there are about 10 questions that are
Yeah, I went through the first co-reference. I said that we can understand. Okay, that was. Can you please post Slack channel again? Okay, I'll leave it.
I did that.
Okay, so in PyTorch, there is embedding function called nn.embedding. I have a hard time embedding, understanding what it means. Can you shed some light on it? And can you give an example, input and output dimension? How are the weights defined? Yes, smile. What I'll do here for this answer, I'll probably give some particular example. It's hard for me to explain everything on the fly here because I don't have the appropriate slides. I will type the answers for you. It's the person who is asking that question. Okay, I'll do that. So in slide 36, I think I answered the question. Okay, so the matrix W is the embedding. Yeah, yes, it is. Matrix W is the embedding, right. It's like a lookup table. Exactly. You're right. I think you got it right. I think this person, that's a nice chat. I want to just make sure that I convey that information to the people. So if you think about it, this W is the list of embeddings. So right here, this W is the list of embeddings, right? It has got 6 embeddings because our whole vocabulary is only 6 here, right? Only 6. Why 1, 2, 3, 4, 5, 6? We have only 5. 1, 2, 3, 4, 5. This is 6th one coming from. This is not 0.2, 0.2, 0.3 is not part of it. Only this one. Starting from here. And this is basically your W word embeddings, and this is like a lookup table. You're right. Which is hard coded, so every word has got a number associated with that. The hard coding is so nice enough. If you multiply the hard code with the word embeddings, it will just pick the right one, your own embeddings. That's how it is structured. It's kind of cool from that perspective. So we're all spot on here. Instead of having one hot encoding for each word, why not just do a table lookup for the word embedding? Yeah, you can do it, but think about the setting up a deep learning network. It's pretty easy to do a deep learning network if you represent it as a matrix, right? The one hot encoding lets you represent everything as a matrix, and you don't have to do table lookup and everything. Just do a matrix multiplication, you get what you want. That's the idea. Okay, and if you can set it up using table lookup, go for it. But this is the way. It's easier to do it using matrix multiplication, forming equations, and using regular deep learning representation of data, right? Can these slides be shared with us? I think I can. There's nothing proprietary here. This is a collection of information from a lot of different things. I'll work with Yash on this. We'll just send it over. Yash can do this piece. Same question again. Will the slides be shared? Yeah.
We'll see if you can just post it on Slack.
Yeah, there's nothing. These are all information available all over the place. A collection of information. That's it. So let's go to the demo.
Yeah, a
Go
couple
ahead.
of other quick things jumping out on Slack. I don't know if you're on there, Ravi, but uh, question is, word embedding sizes are bloating up really fast in production. What are the techniques for memory efficient word embeddings?
So why do you make this comment? It's bloating up so fast. So word embedding sizes, right? So it's a good thing, right? The shorter the sizes are, your computation is going to be smaller, right? Short, lot less. And if it is longer, of course, um, your computation is a lot more. I see embeddings as this, right? Um, is it's shorter. You can use that as a as a um, learn basically a variable when you're actually using your developing your model, and see what is the minimal size will get you what you want, right? You can actually tune for that particular piece. That's how you should do it. And I see variables, more variables you have, it's actually creating more dimensions for you, right? That's what is happening. One dimension could be to see whether this word is having can define the sex of the word, male versus female, right? It's two different sex. Maybe one particular definition will that one of the vector terms will catch this, right? Another one could catch whether it's a city or a country, those kind of things. These are different dimensions which will capture different meanings of the word, right? That's why you give it dimension. You just say one dimension, you give it 10 dimension, 15 dimensions. Go and differentiate yourself in these dimensions. So more you give, you can more easily differentiate among itself. But if you bloat it too much, it is taking too much time. That's now number one, to process it. Number one. Number two is, it's very difficult to differentiate certain words if you just mm, uh, give too many dimensions. So you have to come up with some kind of optimal way of doing it. One way to use it is to tune your model and keeping this as a variable and see what is the best size which will fit it. Again, as I'm telling you, these are all getting out of our hands now. All the pre-trained models, people have done a lot of research, and they have come up with the best possible representation of the embeddings, and we just have to use it, right? Which is a good news. Good question. What else? Is a vector for a word specific to a language? It is just a vector representation of the word. It is not specific to a language at all. In sense, it includes the language context too, right? Because the word by definition is parts of the language, right? For example, can in one language has the same vector different from that of another language? Probably it can, right? If you have a can as a word in English and can as also a word in some other language, probably it will have a different vector, right? Probably it will have, because the context it is used within that language is completely different from the other language, so the representation will be different. What else, right? Think about this. The word embeddings are typically within the context of a specific language or a specific spoken language. Let me put it that way, because a spoken language could normally combine words from different languages. Okay. Then one, is it recommended to work with pre-trained embeddings or task-trained embeddings? Very good question. So I would start with pre-trained embeddings and let it, if you have enough data, and let it train further using a supervised training mechanism, right? That's what I would use. But I will try both. First, I'll just use the pre-trained embeddings and let your other weights in your deep learning network get trained using your supervised machine learning method and see how it behaves. Then let it also train or change the word embeddings and the pre-trained word embeddings to see whether that behaves better. My gut feeling is, if you have a pre-trained embeddings from BERT or some um, um, large network, right? Trained using a large network, you're probably better off using it because they have gone through the pains of training this using much bigger data set. And any other information you want to derive out of the words based on your context, you can get it using the other network aspects of your model, right? You can do that. All right, so good questions. Let me go on to my demo, which means I have to stop sharing and again share again. And one second. I hope you can see my screen here. Can you see my screen? Hello?
Sorry, Ravi. Yes, we can see your
The Chrome
Jupyter.
screen.
We can see the Jupyter notebook. Yes.
Oh, great. So this is not really a PyTorch tutorial or something. This is, I'll just go through a typical PyTorch program. How does it look, just to get a feeling of how it is. This is a simple classification program, right? So if you see here, this is, we are loading all this import, all the modules, and we are loading the text here. In this case, it is diabetes data, which has information on some information on the patients who has diabetes or who also doesn't have diabetes, right? The symptoms information. So you actually create a data set, diabetes data set, which will generate this data for you. This is the training loader based on the data set. The model definition will look something like this. It's nn.module, torch.nn.module, which is the base class for um, a model, right? Deep learning model, which has got an init where you define the different layers which is going to be used, and the forward pass is where you define the sequence of layer. For example, the first one is self.L1, which is nothing but a linear layer having 8 as input and six nodes as output. Then that gets passed on to activation function called sigmoid, and that becomes out. And you can just read this. The out becomes the input to the next model, which is next linear model is 6x4. And the output of that will be passed through activation function of sigmoid, and it becomes that out 2. So you can draw the network. This is the network. This is what it goes through. This is the prediction. And the backward propagation is not shown here. It's part of the base class. It takes the your prediction and compares that with the here. If you see that the way it is set up here is you set up the model. This is your optimizer, right? This is how you optimize the parameters based on the differences between the Y prediction and the labels. And your network, in terms of training the model, is very straightforward, right? You take the prepare the data, which is inputs and labels. Inputs are nothing but the diabetes patient's information. Labels are nothing but whether the person has got diabetes or not, right? And take the inputs, run through the model. It comes a prediction is Y prediction. These two needs to be compared, whether it's good or not, right? This is the comparison is being done. Where is the criterion? Criterion is what kind of loss you generate in terms of comparing these two prediction and labels. And the loss goes through a backward propagation. This is all defined. As part of the loss backward propagation, all these weights in these the linear networks and everything will get adjusted. And finally, you'll get a nice model. That's the idea, right? Then you train this for 50 times. And if you see what's getting printed, the loss is getting printed. It's getting lower and lower and lower, hopefully. Yeah, after that, it's kind of stabilized. And I stopped here, right? This is how the typically a PyTorch training works, right? You have a data set, you define a model, what it goes through, you define how the loss functions are generated. Then you go through a training step to optimize your weights on the model. So having said that, let's go through a sequence classifier, right? Let me see. I ran this _1. Yeah, this is the one. This is a live one. I just ran it because it takes some time to run it. Let's go through this. A sentence classification, right? This is our NLP model. This is all kind of wonderful um, um, embeddings here, right? Sentence classification and sorry, this is all the imports which are being done. Here, what's happening here is you take the load the data set, and it is actually defined in load data set. It's demo STM load data. Okay. See here, so they are loading the data set basically. And if you see that, it's the embeddings are getting loaded from the IMDb data set. Basically, it is after seeing the movie, whether it's a good movie or bad movie, right? I believe that's what it is. You get that particular information, and you also get the word embeddings. It's also from a pre-trained model. So you get the word training embeddings also, right? That's also we have. So all these things are already defined as part of the Torch text dataset. We're just going to use it from there, right? And the vocabulary is from the GLOW. GLOW is a pre-trained model, right? It's taking the vocabulary, and as well as the vectors is the nothing but the word embeddings. It's also coming from the GLOW model. It's a pre-trained model. So basically what's happening is all these, everything is set up for you. The word embeddings has been set up. The text is already there. The result, whether it's in terms of sentiment, whether it's good or bad, that's also already defined. Okay, so we're going to take these sequences or sentences, and then, so length of the text vocabulary is like this is a pretty long, pretty big data set. Vector size is this, right? By looking at this, can anybody say what is the word embedding size? 300, right? This is the W. Remember the W matrix we saw? That's what it is. There are so many words, and this is every word has got a vector of size 30, right? This is the embedding length. Embedding length is 300, right? That's what it is. And we are building this model called LSTM classifier. The model is very straightforward. It takes the word embeddings. That's the W1, right? It takes it, and it goes through a LSTM network where it has got 256 LSTM, right, boxes, and 300 is the input which is coming through, and it's going to take it, and the last layer is a linear layer which is going to take this and produce an output 2, which is yes or no, right, good or bad. It's a classification model. It's a pretty straightforward network. Network is pretty straightforward. The word embeddings is already given, right? It's already given, and use an LSTM network for just training it. That's what you're doing. Okay, don't worry about this. This is too short of a time frame to see everything what's going on. You just get the idea about what's going on. It's fine, right? If you, as part of this 1.5 hours, 1 hour's time you spend, if you get a good idea about what NLP is, what word embedding is, if you grasp that, internalize that, that is a great good thing, right? So you train the model. It's very similar to the one I just showed you before. You take the training data. Then this is all for using your GPU and other things. Your prediction. This is your forward pass, right? You take the model, take the text and pass through that and get the prediction in, right? Then you compare the prediction with the target. Target is nothing but whatever that they've already given, right? Kind of see the differences, and do the backward pass is where you go and adjust your weights, and you keep doing this multiple times, right? And evaluation of the model is do the same thing, but you want to check for the result. Don't this is not training. You want to check with how well it is doing. It's what it is doing. These are the functions, and this is actually where the training is happening. And here are the results. Training accuracy of the first epoch is like 40s and 70%. And the validation accuracy is from a validation data set. It's a 56%, which is not all that great. Epoch 2, it has given better. Here is 72, it's getting better, 75, 80, 80, 81. So it's kind of stabilized, and we stopped here at this point. You can see that as the training accuracy is getting better and better, but the validation accuracy is kind of stabilized. So 4 out of 5 times, you're getting it right. Okay, that's the idea. So this is a typical LSTM sequence classification. We call it sequence classification. It's nothing but a sentence classification, right? It could be a sentence or it could be a paragraph classification based on LSTM. And what the technology was being used is word embeddings. It's called pre-trained word embeddings. And then you start using the LSTM model for doing it. I think here somewhere in this case, I have to look into this carefully. I believe the word embedding starting point is from GLOVE. And as part of this process, the word embeddings is also getting changed. I don't think we froze anything here. We did not. We did not freeze it. We can freeze it if you want, but we did not freeze it anywhere. Anywhere it's getting freezed. All the parameters, no. Everywhere, I don't think. No, it's not getting frozen, which means the answer to one person's question there is, what are we doing? Are we pre-training everything here? We are not training the embeddings here. We are still using the GLOVE pre-trained models embeddings as a starting point. And then we are letting this network train those embeddings too, because it's not going to change everything upside down, but it's going to switch it a little bit here and there so that the embeddings are more amenable or more geared towards the current context, which is the movie ratings. Okay, so that's a simple example of one LSTM, but LSTM is going away, right? I don't have the time. I just give the LSTM is very difficult to train, and the longer the sentences, it's tough. Main problem is difficult to train, and it needs it doesn't use. You can't do a lot of parallel processing because again it's all sequence based training, so it's slow. So all those wonderful drawbacks are there. So people came up with something called transformers. The transformers based network is very good in terms of parallel processing, so you can train lots and lots of data parallelly, and most of the modern pre-trained models like BERT, GLOVE, and other things, they're all based on transformers. So I'm going to show you an example of a transformer, which is a pre-trained model. Then if I get a chance, I'll go back to the slides. Okay. Let me here, LSTM, go here, BERT. I can show you some certain things like this. Sentence completion. So in this case, it's using GPT as the it's like a time. GPT is a pre-trained model. BERT is a pre-trained model. There's a lot of pre-trained models, but GPT is one of them. It's all based on transformers, right? And here, what it's doing, it's finding the next word. That's what it is doing. We're just using the pre-trained model. We're not training anything here. If you see here, you're not training. There's no training. We're just using it. I just loaded the pre-trained model. This is the tokenizer. This is the model, pre-trained model. I just loaded it. And it's going to find the next word. So it's going to take, for any given text, it's going to make it a token. The token is converted into a tensor. This is all CUDA tensor. This is all it's nothing transformation. It's just converting the variables to make sure it can work on GPU. This is the model execution. It's no training. It just takes the input text and runs through the model, gets the output, and from there it gets a prediction. And from the prediction, you can convert the prediction will be what? It will be a kind of a token, right? From that token, you have to come up with the text, which is what it's doing. From the token, it's decoding the token and coming up with the text. That's what it's doing. So see this one. What is the fastest car in the answer is world. Came with nicely, right? Are you available today evening for? The next possible word is A. It came up with that word. It's a nice sunny. It's a nice Sunday, a sunny day, right? I cannot cook dinner today. Can we order pizza for? The next word is dinner. So in this case, The beauty here is, I have only 7 minutes, but I just want to get it across to you, right? We talked about word embeddings. So what are we doing with word embeddings? It's all part of this particular model, GP2, LM, LN2, LM head model, right? So it's got everything is all done for you, right? And they have this particular setup, a model which will predict the next possible word for a given sentence. So you can just use it, just take it and just use it. And you can find this is, you can just do it. It's not a lot of code. You just start using it. You're not even doing any training. You don't need GPU. It's a regular thing. You can do it. Where all can you use it? There are different ways. We can use it for when you're typing in an email. It gives you a lot of predictions for the next word. There it is, right? You can do that, and you can actually do this continuously so that you can start generating sentences. You can do that too, right? So you can take this, use dinner, and then go and predict for the next word. You can keep doing it, and you can come up with meaningful sentences. So this is the beauty of it. We have come a long way from defining word embeddings and making it work and training and other things, just using an out-of-the-box model. This is one example. Okay. What else here? Classification demo. What is this? So here is, let's move backwards. So here you take a text string, right? This is Treasury Secretary Steve mentioned. This is not this year, by the way. This is last year. I took it from somewhere. Take that one, and it basically contents us to see what it is. It says this is world news. That's what it is doing, right? It just says it's world news. Here, John Memphis, what is this? June invitation of the story, blah blah blah. It read through the whole sentence, and it said this is a sports news, right? The idea here is somebody is sending a lot of text. You can actually categorize the news to different sections. World news, sports news. In Yahoo, if you go, it categorizes the news in different format. This is how it's done, right? And let's see what they're doing here. Actually, here in this case, actually we are actually training the model. That's what we are doing. And now that you know all about this, let's take a look at what it's doing, right? This is the data set. And we have got this, this is the model we are doing, right? Text sentiment. This is the network. And basically we are taking the text, creating an embedding. And this is embedding, it gets embedded. Basically, the embedding doesn't mean that it has got the weights for you. You can create this embedding can, I think this is the answer to the person. Somebody was asking NN dot embedding, what does it do? The embedding means it creates an embedding for you with certain vector size. Maybe you can initialize it with a random variable, but doesn't mean anything. You have to train it to make sure it has got the right weights. It's important. That's what it's done. It's doing the embedding, and from there it's running it through a fully connected layer to give you an output. That is what it is doing, right? The embedding dimension is 32, and this is all generation of data. This is the training, right? So you get the data, and you manipulate the data to get the text you want, and run through the model, right? Text output comes in, compare the output to what should be the output, the classification of that particular news, and do the backward propagation, train the model. So in this case, we are not using any pre-trained embedding. We are actually creating a basic embedding data structure, which has got some random weights, and actually training it. And this is the result you get, which is not bad at all, right? It's not bad at all. It's a function of good data. I think we got good data. The accuracy is over 90%, which is good. All right, so I'm going to stop here. Actually, I want to show you BERT, but that's fine. I think you get this probably, I hope this 1 hour plus was useful for you to get an understanding of where the technology is going, capability of the technology in terms of NLP, what word embedding means, at least that we talked about a lot. What about word embedding? How word embedding can be used along with PyTorch to create a model from scratch, this is like a text classification model, right? We saw that. And also how we can use a pre-trained model where we don't have to, we can just use the already embeddings available and do some tricks like finding the next word, finding those kind of cool things. You can do it right without any training. And much more the capabilities are available using pre-trained models like BERT. If you register for the course next week, I think it's a fundraising event, I think 3 hours, we will go through more details on solving these problems. And the people who will be attending those 2 sessions, you will have your versions of instances of Jupyter notebooks. You can play around. Actually, you get the chance to do this all yourself. The best part of learning is by doing, right? That's the key. With that, I'm going to stop here. Yash, you want to say anything? I'm just going to the Q&A here.
Yeah, thank you. I just posted the URL for next week's workshop on chat, and we're going to offer, I've also posted a survey for today's workshop, and if you fill it out by the end of today, you can add on, I believe it's a very lucrative $5 discount for the workshop next week. So please let me know, and all the respondents who sent that thing and share your email, I'll be sending you the code tonight or early tomorrow. And Ravi, from Slack, I don't have any other additional questions.
I have some questions here. I'll just try
So
to
we can
finish
go
it off
through
within
that.
a minute. Go from the top. Everybody's asking for sharing the code and other things, so we'll do that. Let me see. The code, if it is completely, I'll share, but the slides for sure I can share. It's not a problem. Can somebody explain me what is the difference between PyTorch? When you choose PyTorch versus TensorFlow? I prefer PyTorch. It is more intuitive, and it's used by pretty much from a research standpoint. Everybody uses PyTorch, and if you see any research papers coming out, there will always be a PyTorch model out there. So it's very easy to use when compared to TensorFlow. TensorFlow is they say that I used to use TensorFlow and Keras, but still PyTorch is my favorite preference, because lots and lots of community support is also available. When you productionalize it, you have to do certain things to make sure the model works. But PyTorch is a way to go, from my perspective, on learning and creating all wonderful things. Let me see. In the first notebook you showed, I think I saw loss, optimizer, loss backward. What class contains the weights for the neural network? I thought the training data will be needed for backward propagation. Where is the training data variable above? So the training data is basically consumed by if you see, there will be a statement called output, something along these lines, output equal to model within parentheses the input, right? The input is the training data and the labels, right? That's what it is. Not the labels, the input is the input variables. That's where the training data comes into picture. Output is what the model gives as a result of our propagation. Then if you go and see the loss criterion, Y prediction is nothing but which is the output of the forward pass, comma will be the label, right? The corresponding label in the training data. So that's part of the training data. So you get the loss. And in terms of weights is part of the neural network setup. That's what is there in the basic class, which was subclass from NN dot module. That particular class has the network definition. And when you see a fully connected network or embeddings, that network has got nothing but it has got weights. Basically, it has got parameters. We call it parameters. You can actually look at some parameters and see what the parameters are. We'll go through all those things in detail in the next class, or you can do it yourself. So it's all there. PyTorch, that's why I like PyTorch. It's all there. You can easily see this happening. It's very intuitive, right? Very, very intuitive. Let me see. Can the transformer-based embedding be relied upon to do a good job if my domain is highly specialized technical area with an enormity of terminology not generally available in corpuses used as training sets for language models. In situation that is, am I better off in computing the custom embeddings? Yeah, I think the thing we talked about this, if your domain is highly specialized, I would start off with embeddings, pre-trained embeddings, and let your current network, um, um, let your embeddings be trained further using your current network and see. And of course, there's no right or wrong answer to this. I think that will behave better, but you have the answers, right? You see the results for yourself. You take a look at the accuracies, compare the accuracies of two different models, like what a data scientist will do, and pick the best model approach, right? And also choose an approach which is long-term good for your company too, right? If a pre-trained model gives you all the answers, go with it. You don't have to do much more than that. Okay, that's pretty much what I have. Oh, okay, one more last thing. Please mention again, what is the name of the class that contains the parameters in the neural net? Oh, class. So your module, let's see. NN.module is the module. And if you had to go and take a look at the objects, the layer object, oh yeah, that's right. The model.parameters. Just take a look at the model, whatever model object you created, dot parameters. That should give you all the parameters. And you can actually go and see whether it is trainable, not trainable. You can do all those kind of wonderful things. Dot parameters. Okay. All right, that's pretty much what I have. It's 11:35. I think we took 5 minutes more, and hope this is of some use to you, because thank you very much for joining on a Saturday. That shows you the passion you have for the technology. This is the Silicon Valley spirit, and wish you the best. Thank you. Have a rest of the weekend. Good rest of the week.
Fantastic. And I'm going to share the URL to the survey right here in the chat once again. So folks, please respond to it, and you should have it in your inbox as well. But do consider giving us feedback, because this is how we improve the quality of these workshops, and this is how you get the specific training, right, that'll help you in your job search. NLP is the fastest growing subdomain of deep learning. It's impacting finance, legal, you name it, medicine. And so it has a very broad set of applications. And I work at Intel, and we are seeing this day in and day out. And once you are, comfortable with the higher level and implementation level details of, say, something like NLP, you can go ahead and start learning more and more about the architectural constraints, like such as, where is it compute optimized, where is it memory optimized, and what you can do to say reduce accuracy for better compute performance, and vice versa, right? So thanks again, everyone. It was lovely having you here, and hopefully see most of you in the workshop next Saturday and Sunday. Take a look at Eventbrite and reach out if you have any questions. Bye-bye. Thank you, Ravi.
Thank you. Bye.
Okay, thank you, everyone. I'm going to end this now.